Hi everyone, my name is Holly Andrews. I'm a postdoctoral researcher at Chalmers University of Technology, and today I'm going to be talking to you about what's up with Betelgeuse and what might it do next. So what is Betelgeuse? Betelgeuse is a massive star in our galaxy, otherwise known as a type of star called a red supergiant, or RSG for short. It's located in our night sky in the Orion constellation, along with other massive stars such as Rigel, a blue supergiant. But Betelgeuse itself is one of the brightest stars in our sky, and usually is actually the 10th brightest star in our sky when looking up at the night sky. And it's also very close to us. So if we consider the entire galaxy to be about 100,000 light years across, Betelgeuse itself is only about 700 light years away from us in distance. So what is a red supergiant or an RSG? These are massive evolved stars in our galaxy. And so we can try and consider different types of stars that we see when we look at the night sky by considering the Hertzsprung-Russell diagram. So this is a diagram or a tool that astronomers use to try and classify different types of stars. So a star like our sun is known as a main sequence star because it lies on this central strip or line that you can see in the picture showing the Hertzsprung-Russell diagram. And these are stars that are stably converting their hydrogen fuel in their cores to helium, and so they're converting that, and that will take a few million or billions of years depending on the size of the star. But when they have converted all of that hydrogen fuel in their center to helium through the process of nuclear fusion, they are then able to start converting helium and other elements to even heavier elements such as carbon, nitrogen, and oxygen, all the way up to iron. So when this process starts occurring of these heavier elements being synthesized, this also means that the envelopes of the star expand outwards and the star actually becomes slightly cooler, but also brighter. So in comparison to our sun, which is 6,000 degrees Kelvin, red supergiants are relatively cool at about 3,500 Kelvin, but they're also a lot brighter as well. So if we consider where the sun is on this Hertzsprung-Russell diagram on the main sequence, we can also consider that Betelgeuse would occur up in the right-hand top corner because it's very much cooler, but also much brighter as well. So a little bit more about the properties of these red supergiants, or these massive stars that we see in our galaxy. They are much more massive, as I've already said multiple times, and so they actually start off their lives with up to around 20 times as much mass as our sun. Although by the time they become red supergiants, they have lost some of that mass through their enhanced stellar winds and outflows. And these enhanced stellar winds and outflows occur a lot during the phase of their life that they are these red supergiants. As well as this, they're also cooler, as I've said, but also brighter, and in fact can have luminosities or amount of brightness 100,000 times as much as our sun. And they exist in these phases of these red supergiants as opposed to that main sequence phase I talked about earlier over a time period of about 100,000 years, which may sound like a long time, but when you consider the total lifetimes of stars like our sun to be about 10 billion years, or even these massive stars which have quicker lifetimes to be about 10 million years, 100,000 years is a relatively short amount of time for these stars. And we also have an image here from some ALMA data. So this is actually showing Betelgeuse itself, and you can see how much bigger they are than stars like our sun, because we've got to scale the relative sizes of different orbits of planets in our solar system. And so in fact, Betelgeuse as a star, if you put it in our solar system, it would expand outwards past the orbit of Jupiter. So when considering these massive evolved stars, it's also useful for astronomers to think about the different processes and stages they go through over their stellar lifetimes. Stars can be classified into two major groups. So these are smaller stars, stars like our sun, or larger stars. And so the divergence between the types of evolution and types of lifetimes that these stars experience occurs when stars are at least 8 to 10 times as massive as our sun. So for stars that are more like our sun, when they have finished burning all that hydrogen fuel into helium, they will then become what's known as a red giant. And so they'll experience that process that's similar to what Betelgeuse experiences, where it has expanding outer envelopes that expand and the star cools down a little, but in the core, they're still synthesizing heavier elements. And so this leads to the production of elements such as carbon, nitrogen, and oxygen. And so at the final end stages of a star like our sun's lifetime, it's going to be left with a planetary nebulae, which is all these outer layers of the star having expanded outwards and being thrown off, but also a white dwarf that will be left behind as sort of the remnant of the stellar core. And so that will be made up of these elements such as carbon, nitrogen, oxygen. But unfortunately, it's not hot enough to synthesize any heavier elements, so it just starts to slowly fade away. For more massive stars like Betelgeuse, things are a little bit more exciting, at least in my opinion. And so you have a large star, as I said, at least 8 to 10 times as massive as our sun. That will then become what's known as a red supergiant. And in some cases, they get so massive and so luminous, they can be what's known as a yellow hypergiant. But for the purposes of the talk, we'll focus on red supergiants like Betelgeuse. And so they have these expanding outer envelopes, but they also have this core, and in massive stars, they are actually hot enough to synthesize elements all the way up to iron. And so eventually what happens is the star is unable to win this battle that's always going on between the gravitational forces going inwards and the radiation pressure caused by creating these elements going outwards. And at this stage, we get what is known as a core collapse supernovae. And so this is a giant explosion. And so what you're left with then is a supernova remnant of all these outer layers that have been exploded outwards. And you get two different types of stellar remnants for these massive stars at the endpoints of their lifetimes. So these can kind of take two different shapes. They can either be neutron stars, and so these exist for stars that are around 8 times as big as our sun, up to 20 to 25 times as big as our sun. And these are very, very dense, very, very small objects, and often they can be rapidly spinning and so lead to repetitive electromagnetic signals that we get from these stars, and these can be known as pulsars. Or you can get the exciting objects known as black holes, where in fact the core collapse was down to a size that's so small and the gravitational force of this final remnant is so strong that you're left with a region in space-time where not even light can escape past the boundary known as the event horizon. And so these are very difficult objects to observe, but here I have the image in the bottom of the radio observations made of the areas around a black hole that were taken last year with the Event Horizon Telescope. But back to Betelgeuse itself, which is in the red supergiant phase of its stellar lifetime. So Betelgeuse is actually known to have a variable light curve normally, and it's what's known as a semi-regular variable star. As well as this, although we like to simplify our ideas when we think about stars, Betelgeuse does not have a smooth or uniform surface. And so it's important when people develop models of Betelgeuse to be aware that its surface is constantly undergoing forces from the magnetic fields, but also the convective fields that lead to variability on its surface normally. So here we have a model that has been created trying to demonstrate sort of the different dynamics at play with how Betelgeuse's surface can vary. So as well as this, here I have a light curve for you all of Betelgeuse. And so as I said before, Betelgeuse is a semi-regular variable star, but last year, and as you can see, there's this massive dip, Betelgeuse actually started dimming even more than usual. And so by mid-December, as I said before with Betelgeuse, it is usually the 10th brightest star in the sky, but actually by mid-December last year in 2019, it was only the 21st brightest star in the sky. And so this was a bit of a question for astronomers, and it was important for them to try and figure out what exactly was going on with Betelgeuse. So back in September, there were actually observations taken of Betelgeuse that showed it was hotter and brighter than normal, especially on its surface, known as its photosphere. But by February, it actually lost 2/3 of its normal brightness. And so here we have some images from the VLT, or Very Large Telescope, showing not only the differences that can be seen in the brightness of Betelgeuse, but also in the shape and the morphology of Betelgeuse's surface. So it's quite subtle, but hopefully you can pick it up when you see the difference between the January and the December pictures. So why was Betelgeuse getting fainter? So astronomers sat down and lots of different groups of people tried to consider the different observations they had and the theories you could have around why this was happening. So one of the ideas around why Betelgeuse was dimming and getting fainter was that it was just a coincidence. So Betelgeuse, as I said, is a semi-regular variable star. So it has this variability in its light curve, as we saw earlier. But actually, it's got two different variability timescales that go on. So it's got a short timescale over which it varies, and this is a 425-day period of variability. But it also has a longer period of 5.9 years over which its light curve varies. So some people considered that maybe this is just intrinsic to the star's stellar variability in its overall light curve, and so it had reached an absolute minimum. But this was considered to be probably not the full story. And in fact, when we consider the star with different parts of the electromagnetic spectrum, so not just the optical light, so that's the light that we can see, and in fact the light that we could see Betelgeuse with if we look up at it in the night sky, but also the many other different parts of the electromagnetic spectrum as well, we can measure different types of light that we see from Betelgeuse. And in fact, Betelgeuse, being the 10th brightest star in the sky, optically is actually the brightest star in the sky in the near infrared. And so people considered, had it changed in the infrared as well as in the optical? And so they looked at this type of light of infrared observations from Betelgeuse over the past 50 years, but they found that the brightness did not change and it remained fairly constant. And so the brightness change that we did see in certain parts of the electromagnetic spectrum for Betelgeuse are not due to a change in the brightness of the star itself, but rather an effect occurring due to phenomena on the surface. And so a couple of different theories about what could be happening on Betelgeuse's surface were then put forward by different groups of people in the astronomy community. So before we go into those two different theories, a big thing that happened in the news media is people heard Betelgeuse was dimming and they thought, could this be the year that Betelgeuse goes supernova? And although there have been a lot of news stories this year, this is actually an unlikely one to come true. So Betelgeuse is expected to go supernova sometime over the next 100,000 years, because as I've said before, red supergiants are only expected to experience that phase for 100,000 years. But why would we expect it to be now? So we actually don't think that now is a likely time for Betelgeuse to go supernova. And as we believe that this brightness change is due to the surface of Betelgeuse where something's changing rather than the underlying core part of Betelgeuse itself, it's unlikely that Betelgeuse is actually going to become a supernova as a result of this dimming. And in fact, as Betelgeuse throughout 2020 started to increase in brightness again, this only supported the fact that this dimming is related to a change in the surface of Betelgeuse rather than an underlying final dimming event before going supernova. But as a fun fact, when Betelgeuse does become a supernova, which we can't predict when it will do with accuracy, it will be bright enough to see during the day here on Earth. So it would be a very exciting astronomical event. So the two different theories that people have put forward in the astronomical community about why Betelgeuse went through this dimming event is, one was that it could be obscured by these dust spots obscuring the star. So this is supported by the fact that Betelgeuse became brighter in the ultraviolet as seen by measurements taken by the Hubble Space Telescope looking at magnesium lines. And so, as I've said before, it was seen to be brighter and hotter on its photosphere in September before then dimming in December to January and February. And so from this brightening being seen initially, people believed that hot material was ejected into space from the surface of the star, causing this initial brightening. And so as this material then cooled over the following months, this then led to these large circumstellar dust spots, which would obscure and cause the star to be dimming. But this is not fully supported by what we see, because as I've already stated, people looked at the infrared emission from the star, and this is found to have remained constant. Whereas with dust, you would expect it to absorb and obscure in ultraviolet and optical light, but actually to then heat up and emit in both infrared and millimeter types of light. And so as the infrared emission remained constant and the millimeter emission actually grew fainter, this doesn't fully support this idea of these dust spots. And so another possible idea that's been put forward is the idea of large star spots on the sky, similar to the stellar sunspots that we see for our own sun, but to be much larger and 50 to 70% of the visible surface. Although further studies need to be done on Betelgeuse and to observe its light curve to fully rule out or to support either one of these theories. And Betelgeuse itself continues to behave strangely. It was expected that Betelgeuse would actually reach a maximum of its light after it started increasing again after February. And so to then reach a maximum in August or September, and to then go back down to a minimum in its light curve in April 2021. But actually in June and July, Betelgeuse started to fade from April's brightness, where it reached a maximum, and then it reached a minimum in its light curve in August. And this is believed to be another dimming event from another dust cloud emitted from Betelgeuse. So please do watch this space to try and find out more about what scientists are doing to figure out what's going on with the surface of Betelgeuse. And I'd just like to finish this talk by saying thank you very much for watching. Hope you have a great day.